So we continue deriving this eigenstates, including eigenenergies and eigenfunctions of the harmonic oscillator problem by using this operator method. And last time we defined this Hamiltonian of a harmonic oscillator, but in a different way. So we defined the operator A, which is the linear combinations of x and IP, and we've discovered that this Hamiltonian of a harmonic oscillator is given by this h bar omega times A dagger A plus 1/2. So this greatly simplifies our calculation, because we could take advantage of such an operator and their commutation relations with each other and also with the Hamiltonian. Okay, so we proved that this commutator between Hamiltonian and this operator A is given by minus h bar omega times A, whereas in this commutator between h and A dagger, we get this h bar omega times A dagger, and A and A dagger commutator is 1. Okay, and we further show that when we evaluate this kind of eigenvalue problems, where this red circle is the state after we act this operator A onto any eigenstate with eigenenergy E, and we find that this state A acting on E is also the eigenstate of the Hamiltonian, but with the eigenvalue E minus h bar omega, which is you take the elevator down to the one floor down by applying operator A onto any eigenstate E. Okay, so likewise, when we go up floor by 1, so we should apply the A dagger operator onto any eigenstate E, and in the same way that we can show that this state is also the eigenstate of the Hamiltonian H, but the eigenvalue, instead of E minus h bar omega, it is E plus h bar omega, and that is the way that we show this by pointing up just one floor with respect to this starting any eigenstate E. Okay, so we could take the elevator, either go up floor by one floor or go down floor by one floor. Okay, and this is the great advantage of this operator method, because we could actually use this operator A and A dagger. We could actually go from any state we like. For example, we could actually take the elevator down to the ground floor E0, and then we could actually establish some equations by taking the elevator even further down to the basement. But we know that there's no basement, because there's no, suppose E0 is the ground state, and there's no states below E0 state. Okay, so but we could in general take the elevator anywhere we like, but we know that when we want to actually go downstairs, if we are at the ground floor, then we take the elevator down, and there's no place that we can go, which means that when A acting on ground state 0, this should vanish. Okay, and this result sounds natural, but it is a consequence of the fact that the energy of the harmonic oscillator, when we take the excitation value sandwiched by any wave function or any eigenstate, should be always positive or 0, or greater than or equal to 0. And as a result, if you decrease your eigenstate by, say, integral multiple of h bar omega, and sooner or later your eigenvalue may become negative. Okay, but this is not correct, because the eigenvalue or this expression value of the Hamiltonian is always greater than or equal to 0. So you cannot have the eigenvalue or eigenenergy to be negative. Okay, so the reason is that the Hamiltonian, remember, is made of the kinetic energy and potential energy, right? So it is made of this p squared plus x squared, and we know very well that this p squared is the square of the p operator. So all this exponential value of the p squared operator, no matter what kind of a psi that you sandwich this p squared, it is always greater than or equal to 0. And similarly, this x squared, exponential value of x squared is always positive or 0. As a result, you actually sum over p squared and x squared by this coefficient, whatever you the coefficient are both positive. K is positive and m is positive. So everything is positive, so you cannot have a negative eigenenergy. But this elevator can actually take you downstairs, but in general, it can also take you to the negative eigenstates, but this should be ruled out. And this is the reason that we demand when we start at this ground floor and we'll take the elevator down to the basement, it is forbidden. Okay, so you cannot go to the basement. There's no basement. So the ground state energy 0 is the last positive energy eigenvalue that you could find. Okay, so if you go one floor down, the eigenenergy will be negative. And this negative eigenvalue state does not exist. Okay, so, and this is a very simple way to actually find out this ground state wave function, because we know how to get this wave function from this condition. Okay, so this condition sounds natural, but it is a much cleverer way to actually derive the ground state wave function. Okay, so we will get to that in just a moment. Okay, so a second remark is that the ground state, or state 0, does not necessarily to be the zero energy state. Meaning, the 0 refers to the state that it is the ground state, the lowest energy state, but this lowest energy state, in this case, shows the positive eigenvalue, which we call this 0-point energy. And the way that we see this is very simple, because you know that Hamiltonian is made of this stuff, and if the Hamiltonian acts onto the ground state 0, and it is very easy, we could do the algebra, because this A operator actually tried to go one floor down, but the starting point is the 0, say the ground state. So as a result, this A acting on 0 or ground state is 0, so this term vanishes, but there's a leftover, which is the 1/2 times h bar omega times the state 0. Okay, which means that if you go from the very left of the eigenvalue equation to the very right, and you see that the state 0 is the eigenstate of the Hamiltonian, but what is the eigenvalue? Eigenvalue is 1/2 h bar omega. Okay, so you know immediately the eigenvalue or eigenenergy of the ground state, which is 1/2 h bar omega, and this 1/2 h bar omega is a positive value. Okay, so then you get immediately the conclusion that we showed earlier in the previous chapter, that this ground state is not a zero energy state, it is a positive energy state. And this positive energy state is called 0-point motion or 0-point energy. The word 0 point refers to that this is the ground state. Ground state is our 0 point, it's our reference point, where you could actually shift your energy to be 0, but we don't do that. We just call this 0 point. And the 0 point is the point of the ground state. Okay, but the ground state energy is not the zero energy state. It is a positive energy state. And this is a very, I should say, special in quantum mechanics, because in classical mechanics, usually if you are hitting to the ground and the energy is actually 0 because there is no motion. But here we'll see that in just a moment that the origin of this positive energy at the ground state follows immediately by the Heisenberg uncertainty relation. Okay, so indeed, because of this uncertainty relation, we have a non-zero excitation value at ground state. Okay, so let's do it. So we see that this Hamiltonian is made of what? Kinetic energy plus the potential energy, right? So we already noticed that this, when the system is the ground state of a harmonic oscillator, if you evaluate this excitation value of the momentum operator and also the excitation value of the position operator, they both vanish. Okay, just like the ground state of the infinite potential well, you know very well that we have argued already that even in this case, you have, say, a 50% of chance that you find this particle or wave functions on the right side of this well, and another 50% of chance that you find this particle is located on the left side of the well. And so you take the average, and the average position when the particle is at the ground state is actually 0. Okay, and likewise, you will find that the half of this time that this particle actually moving towards the right, and another half the particle moves to the left. Okay, although they have the momentum at ground state, but on average, the momentum operator, on average, is actually 0. Okay, so this does not necessarily imply that the particle is actually standing still. The particle does move. The evidence that the particle moves is not from this first order momentum and position operator, but it comes from the second order, the square of the momentum operator. And you take the expression value of the square of the momentum operator, and if this is at ground state and this p square average it is the same as delta p square, because you know very well that the arrow bar delta x is what? Square root of x square minus x average square. Right? So if this x average is 0, and as a result you take out of the square roots, and delta x is the same as x square average. Right? Okay. So this is the same situation right here. So when we evaluate this p square average, we effectively evaluate this arrow bar square. Okay? And likewise, we could just evaluate this x square average, which is the same as the arrow bar, in determining the position of the particle square. And then we could just sum up these two contributions in a Hamiltonian when we take the average of the Hamiltonian operator, which is the excitation value of the Hamiltonian, which is the ground state energy. Okay, suppose this state on left and right side of the Hamiltonian operator is just the ground state 0, then this is nothing but the linear combinations of this arrow bar square in momentum variables and in position variables, delta x square. But we know very well that this both expression value p square of x square, as I mentioned, is positive or 0. But we know that from Heisenberg uncertainty relations, delta x times delta p must be greater than or equal to 1/2 of h bar, right? So if the expression value of the Hamiltonian at the ground state is 0, which means that the ground state, or the 0 state has the 0 energy. Suppose this is the case, then we violate the Heisenberg uncertainty relation, because this is given by the sum of the p squared average divided by 2m plus the prefactor times delta x squared, or x squared. Okay, so as I mentioned, both x squared average and p squared average are positive or 0, so you add them up, and this sum of these two should always be greater than 0 or equal to 0. Right? And 0 is the lower bound of this summation of these two terms. But then if this h average is 0, but this is sum of this two square average, it indicates that both p squared average and x squared average should be 0, right? So this immediately tells us that both delta x and delta p should be 0. And this is a consequence that suppose we find the 0 point energy is 0, then both delta x and delta p should vanish. But this cannot be, because delta x times delta p must be positive value. So they cannot be both 0. Okay? If both delta x and delta p are 0, then this is actually violated, because 0 is smaller than half of h bar, it's not greater than half of h bar. So this directly violates the Heisenberg uncertainty relation. So, which means that we cannot have this case. So, which means that both x squared average and p squared average should be positive. Okay? So, which means that neither delta x nor delta p could be 0. So, both of them should be positive, because 0 times a non-zero value is also 0. Okay? So, either delta x or delta p should be positive. So then we should take out this equal from this inequality here. So to satisfy this Heisenberg uncertainty relation, both p squared average and x squared average should be positive. It should not be any of this, either this or that cannot be 0. And this actually proves that this cannot work. Okay, so this h average cannot be 0. Okay, so instead, expression value of a Hamiltonian ground state should be positive. Okay, so this is consistent with what we find, that the 0 point energy is positive. Okay, it does not show that this 0 point energy is 1/2 h bar omega, but at least it is consistent with the fact that 1/2 h bar omega is positive value, and the ground state energy is a positive energy state. Okay, so everything is done by this operator method. We don't do it by brute force, but we get everything we need to know. Okay, so this is the power of operator method in quantum mechanics. So let's take a short break. When we come back, we will continue deriving these ground state wave functions by this operator method. In particular, we try to solve this equation bounded by this orange, and then we could derive all these eigenstates and eigenfunctions based on the ground state wave functions. So I will finish this chapter 6 maybe today and start chapter 7 about angular momentum operator tomorrow. Hopefully we will cover Chapter 8 and Chapter 9 by the end of the semester. Okay. 所以现在各位需要慢慢熟悉用这种运算符的方式来理解量子力学哈。那量子力学就已经慢慢的要脱离爬行的阶段哈，要走路，要用跑的，要飞了哈。那爬行的阶段就是还在用 Schrödinger equation 去解一些这个薛定谔的这个波函数的这个方程式的阶段啊。那我们现在已经站起来要走路了啊，接下来要跑了啊。那到学期末就要飞了哈。所以真正的量子力学其实是在从第5章、第6章以后，一直到第10章spin. Okay, good. So let's just try to solve this ground state wave function. After the method. So we know that this is just some kind of the eigenvalue equation, but this is after this operation. This is just some Dirac state, right? So because A is the matrix and the state 0 is the cat state, so the matrix acting on this cat state is also the cat state, right? But what we want to know is actually the Schrödinger wave function. So what do we do? Okay, so remember this Dirac cat state is some kind of an in abstract sense, a quantum state. It could be projected onto any eigenbasis, right? I could project this state 0 onto the momentum eigenbasis or position eigenbasis. Okay, so whatever I like. So then, since we like to link this equation to the Schrödinger wave function, so why not we simply just project this state onto a position eigenbasis, which means that I multiply this Dirac-Bragg state of an x eigenstate on the left-hand side of this Dirac cat state, so we get this 0 times 0 cat state, but sandwiched by or projected by the Dirac-Bragg state, which is the eigenstates of a position operator. But 0 times whatever is still 0, right? However, on the left-hand side of the equation, it gives us something that we want. So let's just try to expand this definition of an A operator in terms of linear combinations of x and p, and we get this, which is 0. Okay, so then this is the linear combination x and p operator sandwiched by this Dirac-Bragg state x and Dirac cat state, which is the ground state of a harmonic oscillator, which we don't know. So the thing that we really want to know is the projection of this ground state of a harmonic oscillator onto the position eigenbasis. By definition, this is the Schrödinger wave functions of the ground state of harmonic oscillator, right? Which we call this U0 of x. Okay, so this is the magic. So when you really project any Dirac state onto any kind of a complete set of eigenbases, you really want to actually read off the wave functions in that eigenbasis. In this case, this is a wave function in position eigenbasis, which is exactly what we call the Schrödinger wave function. So we get Schrödinger wave functions by projecting this Dirac state onto this position eigenbasis. But we need to do this algebra. One is this evaluation of expression values x operator sandwiched between its ground state and the position eigenstates, which is what? Which is x0, because you could actually act this x operator. The left side of this Dirac-Bragg state, which gives you the eigenvalue x, which is the real value, because the x position operator gives you only the real eigenvalue as a position, because the position is a real valued variable, right? So then you get, to this result, and this by definition is x times u0 of x, right? And u0 of x is what we need to know. But this equation contains information that we need to solve for u0 of x. So this is one operation, but second operation, let's just spell it out. So this is this matrix element, right? So the expression value of the p operator sandwiched between the 0 state and x bar state. Okay, so we could do it in a different way, but we could play the same trick that we did many, many times. Namely, we insert the complete set of eigenstates, either the momentum eigenbasis or position eigenbasis. Here, let us just insert momentum eigenbasis right here. So this unit operator is made of what? It's made of this, the p bra times p cat times p bra state, right? So we insert this unit operator, which is made of the complete, this matrix product is a complete set of momentum eigenstates, and we will find something useful. This is given by, okay, so this is what we insert. But once we insert that, we should look at this matrix element in a different way, as I mentioned. So we could circle in a different way once we expand that. Use this unit matrix. We should actually look at this and this, right? So let's just continue. When we look at this left yellow box, we immediately see that this operator p acting on this Dirac cascade p gives you this eigenvalue p times this eigenstate p, right? So this is p times this x in the product of this momentum eigenstate p and multiply this p. 0 in the product, well, immediately that what is this? So this is nothing but u0 in momentum state, right? In momentum eigenbasis. This is the projection of this Dirac cascade, which is the ground state, state 0, onto the momentum eigenbasis, which is by definition the momentum state wave function. But what is this? This is a projection or inner product between this momentum eigenstate and position eigenstate. So we found that. We already did that. Remember that. We have the solution of this matrix element. This is nothing but this plane wave. In the previous chapters, we already derived this inner product between this Dirac, say, cascade of momentum eigenstate and also Dirac broad state, middle position eigenstate. So this px inner product is given by this plane wave. And we should copy this right here. But we could actually rewrite this stuff. Okay, this integral could be rewritten in terms of this kind of a momentum operator, h bar over I d by dx times the same thing, right? Because when we take the differentiation of this exponential factor with respect to x, we pull out this factor of the ip over h bar, which precisely this p factor right here. Okay, so what can we do next? Well, this could be rewritten in terms of the following form. We simply just return to our previous representation of this plane wave. So this plane wave, now let me just put it back. So this plane wave is, again, this is the inner product between the x broad state and the p cascade, right? Good. Great. So now let's just throw away this resolution identity or identity matrix, because now we could just, again, we make this going away. So because this blue circle right here is nothing but the identity matrix, which could be inserted or could be thrown away any place, anytime that we like. Okay, so this is what? This is unit matrix. And we can simply just get rid of this unit matrix, and we get to this final expression. So this unit matrix is gone. So let me just summarize this result. So x p at 0. At the end of the day, this is given by h bar over I d by dx x of 0, right? But what is this? Well, this is nothing but this first derivative of this u0 of x with respect to x. So now we finished this two different calculations. The first one is the definition of u0 from this calculation of x operator sandwiched by the 0 and x. And the second is the momentum operator p sandwiched by the state 0 and x. So we're simply just plugging these two results back to this condition right here, and then we could derive the equation allows us to get this u0 of x. So plugging this, we get this equation. So this equation is identical to this statement right here. But we project this equation, A operator acting on the state 0 vanishes, and this equation is the same as this equation, bounded by red. So, but the advantage of this equation right here is that we could solve u0 of x, because this is nothing but the first order differential equation, which is easy to solve. So you can actually go to your textbook on this differential equation, and you get the solution. Okay, C is the constant which can be obtained by this normalization condition. Okay, so you plug in the solution back to the differential equation, and this can be satisfied. And so we fix this normalization factor C by demanding that this wave function square should be normalized once we integrate over the entire space. And which is what? You could just check this table of integration, and this integral is so-called Gaussian integral, and gives rise to this factor, square root of this stuff. And so that you immediately find this normalized prefactor C, which is this stuff. Okay, and then we simply just write everything here, and we are done. Okay, so this is the ground state Schrödinger wave function of a harmonic oscillator problem. Right? Sounds magic. Okay, so we don't need to actually go through a very complicated calculations such as the, say, Hermite polynomial or a Taylor expansion of an exponential function, or just to guess this solution. Okay, so we don't need to guess. There is no guess. Just solve this condition by projecting this equation onto this position eigenbasis, and then follow this Dirac notation, and you're done. Okay, so as I mentioned, we can go any floor we like by repeatedly applying A or A dagger operator. So now we start from the ground state, and we know ground state energy 1/2 h bar omega. We know the ground state wave function, which is u0 of x, and then we know everything because we can apply a dagger from the ground floor and to get the first excited state, and then second excited state, and any state. So in principle, we're done. But of course, we need to really carry out this calculation to get this general expression for this any eigenstate. So this Dirac cascade n refers to this eigenstate of the nth a state of the harmonic oscillator, which is, as I mentioned, you simply just apply the A dagger starting from the ground floor. You can get any floor you like. Suppose I apply this A dagger n times, which means that I should use this A dagger to the power of n, and then acting on this ground floor 0 state, but there is a prefactor. Okay, normalize the state, and this is in general arbitrary eigenstates of the harmonic oscillator problem. Okay, so the next job is to actually recover this correctly, this normalized prefactor 1 over square root of n factorial. And again, we will play the similar tricks that we did before. This kind of a commutation relations between A and A dagger help us to really get to this prefactor. Okay, so let's take a short break, and when we come back, we will derive this prefactor. 到这边同学有什么问题吗？就是说要用运算符、运算子这个方式来解量子力学的问题呢，是各位同学在这门课里面必须要学会的事情。好，那解这些 one-dimensional potential well 这些都是比较 low tech 的 level 哈。OK， 这样不算是你真正会量子力学。真正会量子力学是要你会这个东西才叫会量子力学。而且所有之后要学的这些量子力学的系统呢，最后还是必须要用 operator method 来解，才会得到任何的结果。那尤其是固态物理的这些系统有非常多的电子跟原子在一个材料里面，那我们很难，真的基本上是不可能去用暴力的去解这些电子跟原子核的Schrödinger equation， 因为有10的23次方这么多的原子跟电子。好，那些 Schrödinger equation 都是互相有关联的哈。那10的23次方的这么多的 Schrödinger equation 的方程式，那用任何的量子电脑也基本上很难解哈。所以我们必须要放弃用暴力去解 Schrödinger equation 这条路。那非暴力的这个方式呢，就是 operator method。OK， 所以量子力学的精髓呢，就是各位同学必须要学会用非暴力的方式来解量子力学。OK， 学不会非暴力，只会暴力的，那就不叫学会量子力学。Okay, so let's just derive this prefactor 1 over square root of n factorial as the nth eigenstates of harmonic oscillator. The way that we derive such a prefactor, again, it comes from this commutation relations between A and A dagger. So we repeatedly apply such a commutator between A dagger to simplify this calculation. So let us just try to do this algebra and see what we get, right? So suppose I act this A operator acting on this nth eigenstate, which is proportional to A dagger to the power of n acting on 0, right? So this is proportional to the state n. Of course, they differ by a prefactor, and this is precisely what we want to do. Suppose I apply this lowering operator, or take the elevator down by 1 floor, then we could just simplify this and see what happens. So when we do this, we could actually repeatedly apply this commutation relation between n and A dagger. The way we do it is just to take one A dagger out of the A dagger to the power of n, and then on the right hand side we get A dagger to the power of n minus 1, but then we could simply just apply this commutation relation, because A dagger is actually A dagger A plus this commutator, right? Yes. Well, we will prove that this is the thing, right? So suppose I apply this A operator acting on any function of A dagger. What I get is the differentiation of that function f of A dagger with respect to A dagger. Okay, but before we derive this conclusion, we don't know what we will get, right? So let's try to derive, the consequence of this operation, right? So the first thing is that we just take out one factor of A dagger, and then we apply this commutation relation. We know that this is what? This is 1 or minus 1. This is 1. Okay? So we know this is 1. Number 1. Okay, not operator 1, but number 1. Okay? And so you know immediately that you get rid of one operator, because this is, if you look at this term, is 1 times a dagger to the power of n minus 1, which is the first term right here. But of course you get the second term, which is the first term right here, a dagger a times a dagger to the power of n minus 1. Okay? But again, we just take another a dagger out of this power to the n minus 1, and then we actually use this commutation relation one more time, which is this stuff in the middle. And once we take one additional a dagger operator out of this a dagger to the power of n minus 1, the remaining power is actually n minus 2. But again, this is 1. Okay, so you simply just take this factor and multiply by a dagger to the power of n minus 2, and combined with this a dagger to the power of minus 1, you get factor of 2 times a dagger to the power of n minus 1, right? But of course you get additional term which looks messy. But that's all right. So you could play the same game repeatedly over and over again. You simply just take one a dagger out of this power, and then play this the trick, this commutation relation. So you then simply just collect the prefactor in front of the a dagger to the power of n minus 1. So after, say, n times, okay, of repeatedly using this commutation relations, you get the final, almost final expression, which means that the prefactor in front of the a dagger to the power of minus 1 is actually n, because you repeatedly use this commutation relation n multiple times. But of course there's remaining factor, which is the very last step. So this operator is actually a to the power of 1, right? So just a acting on 0. We know that a acting on 0 vanishes. So the final result of this operation is actually prefactor n times 1 power less of a dagger, which is a dagger to the power of n minus 1. So then we conclude that this operation, so by applying a operator to any function made of, any operator made of a dagger, the effect is that we take the differentiation of this f function as function of a dagger respect to a dagger. So if you like, this is a acting on a dagger to the power of n. So the result is actually what? The a dagger of n by the a dagger. Just like what you did in the calculus, you take differentiation of this function with respect to a dagger, you get n prefactor times a dagger to the power of n minus 1 acting on 0. This is precisely what we found. Okay, so we generalize this operation. So whenever we applied the so-called the lowering operator a on any function of a dagger, the effect is that we take the differentiation of that function with respect to a dagger. Okay, so this is the lesson. So we could take advantage of such identity and we could derive this prefactor. So suppose I simply just calculate this stuff. We take the nth order differentiation with respect to a dagger of a dagger to the power of n. Suppose I will get something related to the projection of 0 onto 0, because remember, when I take one order of differentiation with respect to a dagger, effectively I simply just apply this a operator. So we take the nth order differentiation of this A dagger to the power of n with respect to A dagger. So I will get back to the state 0 because this is the level structure. Suppose I'm here, state n, which is made of A dagger to the power of n, right? Okay, and then I applied operator A n multiple times. Then I should get back to 0. Right? Okay. So let's just check. But there's a prefactor. So we will just finish this algebra. And this is what? This is 0, A to the power of n, A dagger power of n, and 0. So then you take the nth differentiation, but you could do it one by one. So I could simply just separate this operation n multiple times. Okay, so I could do it one by one. So when I take differentiation one time by applying this A operator onto this A dagger to the power of n, I get the factor of n, right, times A dagger n minus 1. But then I could apply the second, say, lowering operator A. In that case, the power of A dagger is already n minus 1. So then the second differentiation is this. Give us what? N times n minus 1 times A dagger to the power of n minus 2, right? So I could just keep going, take this n's differentiation one by one. So when I just finish any one of the differentiation, there is a prefactor, and n minus 1 and n minus 2 just emerge, right? So when I finish this differentiation, I get n times n minus 1 times n minus 2, until the last differentiation is actually 1 and then times 0 and 0. And this is precisely n factorial times 0 and 0. By normalization, this is actually 1 because the ground state is actually normalized. As a result, we immediately see that this inner product between Dirac-Brown-Cass state of nth eigenstates is given by 1 over n factorial 0 A power of n, A dagger power of n, which is 1. All right? Okay, so then this is the square of the normalized factor, right? So this is actually the normalized factor, which is the square root of this factor. So we're done. So we successively derive this prefactor, normalized factor, square root of 1 over n factorial, and based on this kind of algebra, that when we apply this A operator or a lowering operator on this nth floor, so we'll get to the n minus 1 floor. But of course, the price to pay, there's a prefactor and in front of this n minus 1 state. Okay, so then we could just do it one by one until we hit the ground floor by applying n multiple so-called destruction operator or lowering operator. So then we demand that this n dotted end should be normalized to 1, and as a result, the normalized state n should be carrying this prefactor. Okay, so this is not magic, but some algebra based on this commutation relation. So now you can see that this commutation relation is the key to quantum mechanics. So when we say construct Hamiltonian and operators, for that Hamiltonian, the first thing we need to check is the commutation relation between all these operators, including the Hamiltonian operator. So once we know these commutation relations, we know almost everything. Okay, so let's just start different formulations on the Schrödinger wave function, the time-dependent Schrödinger wave function. So we should formulate this time-dependent Schrödinger equations in the operator formulation. Okay, namely, we should adapt Dirac notation, right? So suppose psi k state is simply just some kind of Schrödinger wave functions at any particular time. Of course, to make such a link, we need to actually project this Dirac cascade psi of t onto this position eigenbasis, right? And so we get this Schrödinger wave function. So now forget about Schrödinger wave function. So we should use Dirac notation. So to that purpose, we simply just remove this broad state of the position eigenbasis from this matrix element, and then we focus on psi of t, because psi of t is a general eigenstate of a Hamiltonian, and we should look at this time evolution of general Dirac eigenstates coming from this Schrödinger time-dependent Schrödinger equation. Okay, so in other words, this is the wave function or quantum state before we project this onto this position eigenbasis. Okay, good. So of course the solution is this type. In other words, remember this, the corresponding Schrödinger equation is this, right? Suppose we have the Schrödinger wave function psi xt, which is the eigenfunction of Hamiltonian h, and the time evolution of that states from the initial wave function follow this time evolution e to the minus ie t over h bar times this initial Schrödinger wave function. Okay, so but now we could remove this position eigenbasis from the Schrödinger wave function and just focus on the Dirac cascade and how does Dirac cascade evolve, and we should get to this kind of a operator product, which is, this is a matrix because this is made of exponential of a Hamiltonian, and Hamiltonian is the operator, right? So this is the operator. This is the operator in the exponential form acting on this Dirac cascade, right? So, which is another cascade, which is precisely psi of t. It's a Dirac cascade written here. So now this time evolution in Schrödinger wave function in the Dirac notation becomes the operator operation, because this is the exponential operator acting on a Dirac cascade, which is another Dirac cascade, and this Dirac cascade is the time evolved quantum state starting from this initial Dirac cascade. In other words, suppose we find the initial wave function, the initial Dirac cascade, and to know this any arbitrary the time evolution of this initial Dirac cascade, and we should perform such evaluation. So we should really perform this operator or operation. So this tells us that we need to operate this psi of 0 by the exponential operator right here. Okay, and once we've done that, we can project this onto the x eigenbasis, and then we get this Schrödinger wave function at any arbitrary time. Okay, and this is the first time that we encounter such a operator in an exponential form. Okay, so this is e to the sum I h t over h bar, where h is operator. So this is the e to the sum operator. So e to the operator is an operator. So this is some operator acting on this initial Dirac state, and which allows us to time evolve this initial Dirac state to get this, this cat state at any given time. Great. So let's just decompose this exponential operator. So we could do Taylor expansion-like expansion. We could just show that the effect of this exponential operator is the same as this Taylor expansion of that exponent, like this. Okay. Of course, this is highly non-trivial because any exponential function of x is given by this, right? But this x is just a number or variable. But here, this Taylor expansion holds even when x is an operator. Okay, so we need to really prove that, but we don't need much time to prove this. But you could check our textbook that indeed this operator in the exponential form could actually be decomposed and expanded in the same way that we do Taylor expansion for this e to the x function. So, but remember, this series or Taylor expanded series contains infinite number of terms, and each term is actually the operator. So this is, say, one unit operator plus minus I h t over h bar plus this h squared term plus power of n term. So this is the sum of all such operators. So each term carry the power of h, where h is Hamiltonian operator. So let's just try to evaluate the expectation value of any operator b. Suppose, so we sandwich this b operators by this Dirac cat state psi of t, which is the time evolved eigenstates of psi 0. So let's just plug in this. Right, we simply just plug in this psi of t as a Dirac cat state and also Dirac Broad state. And remember, the relation between the Dirac Broad and cat state is simply just Hermitian conjugate operation, right? So as I mentioned, A, say, and suppose I simply just dagger this. This is what and Broad state A dagger. Remember that. But we know that this Hamiltonian is a Hermitian operator, right? So H operator is the same as H dagger. So let me just rewrite this matrix element, right? So I can simply just rewrite this in terms of a Hermitian conjugate of this stuff. And then if I do it, I simply just take the Hermitian conjugate of this e to the minus iht over h bar, which gives us this e to the I plus iht over h bar. Well, of course, h should be h dagger, but h dagger is the same as h, so I simply just remove this dagger right here. Good. So remember, let me just repeat that identity one more time. So suppose this is some operator A, and this is another state psi. Suppose I write this Dirac Broad state like this, and this, by definition, this is what? This is psi Broad state and A dagger. You should really interchange the order between psi and A and put the A dagger right there. Okay? So this, by definition, is what? A acting on psi and everything dagger. Okay? So, and I think this is the thing that you really need to get familiarized, right? So you really need to follow the Dirac notation, Dirac rules, and when you perform such an algebra, you need to remember that this is the Hermitian conjugate of that. And when we take the Hermitian conjugate, the first thing you need to do is to interchange between these two and put a dagger. So let me do it. So this is what? This is, you interchange these two, psi and A, but you put a dagger. which is what? Right? The dagger of a Dirac state is a Dirac state. Remember that. Okay, so anyway, this is your homework exercise that you need to really do the algebra and follow this Hermitian conjugate convention of the Dirac state. So now I follow definition of this Dirac state. I get up to here that I can really get rid of this time dependence from this psi of t, but the time dependence operator instead are in the middle of this matrix element, where you could actually group together the three operators, and operator B in the middle, and on the left and right side of this B operator is the e to the plus or minus IHT over h bar. So we could actually rewrite this kind of a expression value of a B operator sandwiched by this time-involved Dirac states, but we don't time-involve the Dirac state. Instead, we could time-involve the operator. So this is what this equation tells us, that instead we can consider a time evolution of an operator. This operator in the middle could be defined as some operator which depends on time. And this operator, B with a subscript h as function of time, is what we call the Heisenberg operator, the Heisenberg picture. So let's just make a connection between the Schrödinger picture and the Heisenberg picture. In the Schrödinger picture, so we consider this matrix element which we time evolve the Schrödinger states upside from psi of 0, psi of t, and we sandwich this Dirac state of this time involved states, and we calculate this expression value of this B operator sandwiched by this psi t on the left and right side of this operator. But this matrix element is the same as we don't time involve the states, but we time involve the operator. Okay? In other words, we could actually put this time dependence operator and combine this with the operator B, and we can define a new operator which we call this the operator in the Heisenberg picture, which tells us that when we have the Heisenberg picture, this is the definition, that we put this e to the plus IH over h bar on the left and minus IHT over h bar on the right of the Schrödinger operator. But these two calculations are identical, meaning we could either time evolve the quantum state and consider the operator as time independent operator, or we could time involve the operator, but we fix this quantum state at initial time. So either way, okay, is fine. But in many quantum mechanical problems, the operator which is time evolved, or we actually represent the operator in the Heisenberg picture, is actually more convenient. But either way, so we could do it either in the Schrödinger picture or in the Heisenberg picture. So in the Schrödinger picture, so let me just repeat this definition one more time. The Schrödinger picture, the operator does not time evolve, but the state time evolve. And in the Heisenberg picture, we do it in the opposite way, that the operator time evolve, but the state does not. Okay, so we could do it either way. Okay, so we could calculate this matrix element in the Schrödinger picture, where we fix this operator at a particular time, initial time, but we time evolve the states. We could also do it in a different way, that we time evolve the operator, but we keep the state at fixed time, which is initial time. Okay, so you could see that these two approaches are identical. So it means that it's the same thing that you give a monkey 3 oranges in the morning and another 4 oranges in the afternoon, or you give the monkey 4 oranges in the morning and 3 in the evening. So altogether, you give the monkey 7 oranges per day. Okay, but the monkey is actually happier if he or she received 4 oranges in the morning, and he or she is really sad in the evening when receiving only 3 oranges. But that monkey doesn't know that altogether, in either way, 3 plus 4 is the same as 4 plus 3. Okay, so this is the same as giving monkeys the oranges. Okay, so we could actually associate time dependent to either the quantum state or the operator. So either way is fine. But in many cases, the Heisenberg picture sounds more useful. And this is the basis that we would do when we calculate this time expectation value of the harmonic oscillator problem. So suppose that we work in the Heisenberg picture, meaning we fix the state, but we time involve the operator. Suppose we do that. And we ask this question, so what is the equation of motion for that operator? Suppose this operator is in the Heisenberg picture. So suppose B as a Heisenberg operator is defined by this. Okay, so let's just take the time differentiation or time derivative of this B operator. And we know immediately that this gives rise to 2 contributions, right? So because there are 2 exponential operators, one on the left and another on the right. But we know very well that the order matters. Okay, so if you take the differentiation of this operator with respect to time, and you get 2 contributions. One is the differentiation of that exponential plus IHT over h bar. Another is the minus IHT over h bar. And the first term gives you that result. And the second term is this. But you know that this h appearing on the left of this B is certainly different from the other way around when h appears on the right side of B. In other words, depending on whether this h commutes with B, this HB and BH may not be the same. And this is the key of quantum mechanics, that this orders in this, say, operator product really matters. Let's just combine these 2 terms and get this HB operator as function of time minus B of t h. So if you follow the definition and just combine these 2 terms, you get this. But what is this? This is nothing but the commutator between h and bh, right? So this is I over h bar, the commutator between h and bh. And this is what we call the Heisenberg equation of motion, because this is the equation for the Heisenberg operator as a function of time. It looks like this operator really time involved, like momentum operator could be time involved in the Heisenberg picture, or Hamiltonian, or any quantum mechanical operator. So in other words, we could simply take the expression value of that identity, which is given by I over h bar, expression value of h and b. Okay, so this is the Heisenberg equation of motion, and we take the expression value of the Heisenberg equation of motion. In other words, we could use this Heisenberg equation of motion to really calculate the expression value of an operator in Heisenberg picture. For example, this momentum operator or position operator. And next, we will calculate this precisely this too. So momentum operator as function of time, and we take the expression value of that momentum operator, and following this Heisenberg equation of motion, and we should calculate this quantity dp dt, and we take the average value, and also we calculate this dx operator dt, and then we take the average. Okay, but what is this? Well, this is nothing but the expression value of a momentum variable at any given time. Just like a classical variables that you solve the Newton's equation motion for a ball that you actually throw any angle, right, upwards, and then you could calculate the trajectory of that ball in the air, and then finally it actually hit to the ground. Okay, so this is the trajectory as function of time of a classical ball, right? So you solve the Newton's equation motion for the classical object as function of time, but quantum mechanically, this is the corresponding Newton's equation motion for a quantum object. Meaning you could solve this Heisenberg operator as function of time and solve the equation motion for that operator, and then you take the average or expression value of that operator as function of time, and then you get on average this momentum of a quantum particle as function of time, and also the velocity or the position of a quantum particle as function of time. But you need to actually take the average or expression value of that operator. So we will get to that tomorrow, and we'll finish chapter 6. So that's it for today, and enjoy quantum mechanics. Let me just emphasize one more time. Please get familiarized with Dirac notation, Dirac-Broglie-Caste, and Hermitian conjugate of operator, and so on and so forth. And then you appreciate this operator method. Okay, so I'll see you tomorrow.